Hello, welcome everyone. Am I audible? Can you please confirm in the chat if I'm audible? Okay, so we will begin in like 3 minutes at 6:05. It's at 6:05. Oh no. Interesting. Okay, so I think we should begin now. So welcome everyone to Dynamic Programming Techniques. Basically, we will be looking over some easy basic dynamic programming techniques which we often use. So first of all, let's review what we saw in the previous lecture. We saw that programming is basically a technique to solve problems in which we divide our problem into sub problems which are easier to solve. We solve them first and using them we arrive at our solution. We looked at different approaches like top down, bottom up, and saw how they are different and how they both can be useful. So we also looked at some sub problems like uh, when we calculated factorial, Fibonacci series, subset sum, knapsack, LCS, and LIS. So today, let's see. we will first of all do the vine problem, then we will do grid paths, then we will look at partition DP, then we will see how to calculate LIS in nlogn, then we will look at bit masking in DP, and then we will look at exponentiation. So let's begin with the vine problem. So the problem statement is we have n vines in a row. You can imagine like n wine bottles in a row. You can sell each the rightmost one or the leftmost one. Now the price of the wine sold in the kth move is pi into k, i.e. the original price of the wine into the move which it is. So we have to find the maximum sell price we can obtain by changing the order in which we can sell the wine. Constraints are n is 1000 and ai is 29. So let's look at our problem. So basically we simply have wine bottles and we can choose right or left end, and then we can keep choosing, and in the end we will get some cost, or you can say profit, and we have to maximize this profit. So first of all, what can be the most naive approach to this problem? An obvious one is that we take every possible combination of right or left. We are going to make n moves and we can choose right or left, so we can get 2 to the power n moves and we can get a solution in it. But as we can see that n is 1000, so that won't be possible. Now how can we optimize this? One the obvious solution is that we can store the result as this is DP. So we can say that suppose that we have some subarray and we have calculated its answer. Then using this answer, we can calculate the answer of a subarray which has one more element to the right or which has one more element to the left. Uh, let's talk in more depth what I'm saying. Let's see in more depth. So basically what I'm going to say is, suppose I want to find the answer of this subarray. I can find the answer using the answer of this subarray and this subarray. If I know the answer to the first one, then I can say that uh, what are the possible scenarios, that I sold this one and then I sold this subarray, or I can say that I sold this one and then I sold this subarray, and the better one will be obviously our choice. So if we calculate the answer for each subarray, then the transition from the answer of one subarray to another subarray is O of 1, because we have to just take the maximum of two values and both of which can be easily calculated. So as to there are n square subarrays, so our time complexity reduces to O of n square. And as n is 1000, this is a viable solution and we can do with this. So basically we have seen a new type of subproblem in which we are calculating the answer for all subarrays and arriving at the final answer. So we can look at the solution. So we just have to iterate, we have to make two for loops for left and right, and we can see if I is equals to j, we can write the base case, and else we have to take the maximum of two values, either we choose right or we choose left, and finally the final answer will be the answer of the whole subarray. So it will be done in O n square. Fun problem. Now let's move to grid paths, another fun and easy problem for today. So the problem statement is, given an n into m matrix, each element of the matrix is either a dot or a hash, where dot represents empty and hash represents a wall. Given that top left and bottom right are empty, find the number of ways of going from former to latter if we can only move down and left. So let's look at the constraints. The grid size is 1e6. Okay. Any other? Okay, so let's move here. Okay, so what is the question? It says that we have a grid in this grid there can be walls or there can be empty spaces, and we have to go from, where do we have to go? We have to go top left to bottom right. Okay, so we have to go top left to bottom right. Okay, so we have to go from here to here, and we can only move uh, down and left. Okay, so we cannot move in cycles and we can only move down and left, and we have to calculate the number of moves if we move down and left. So how can we do this is that first of all, let's talk about naive approach. Okay, so what can be the naive approach? One very simple naive approach is that you make a move and you keep storing the result in some vector or set or any kind of data structure you want, and you keep making moves. And if you ever uh, we know that we can never repeat any pattern, because no pattern can be repeated as we are only going to go down and left. So two patterns will be different because they will be originating from different parents. So whenever we add two patterns, they will always automatically be different, and this way we can keep adding patterns, and in the end we can get a result. But as you can see, this will be very time taking, as the number of ways can be exponential, and so we will be storing all those ways somewhere, and they will also take some space, so that will be exponential time and space, and that won't pass. Okay, so what better can we do? Other approaches that come to mind is that we do recursion. Basically, we can say that if I want to calculate in how many ways can I approach at my answer, there are only two possibilities, either from here or from here. So I calculate number of ways to get here and number of ways to get here and add them. Obviously, it is important that these two are mutually exclusive, and it is given in the question that we can only go bottom and right, so we cannot go from either to the other, so they are automatically mutually exclusive, so we can just add them. Similarly, for any piece we can add its top and left if they are valid, i.e. we can only add top for this and we can only add left for this, so on and so forth, and we can find a recursive solution. In this, we are not storing anything in a vector or set, and we are not storing our path, so we are saving memory there, but this is still exponential, as if I want to calculate, let's see what will happen. If I will calculate this, then I will have to calculate this, and I will have to calculate this. When I will be calculating this, I will have to calculate this, and I will have to calculate this. When I will be calculating this, I will have to calculate this and this, so on and so forth. Similarly, when I will be calculating this, I will be calculating this and this, and when I will be calculating this, I will be calculating this and this, so on and so forth. As you can see, there are very many repetitions. In fact, it will also be an exponential function and will obviously exceed the time limit. But now the correct solution is very obvious. We just have to memorize our DP as we saw in the previous lecture. I.e., if we calculate the answer for every state once, then we can calculate the answer for every other state in O of 1. And as there can only be 1 states, this will obviously pass. So this is, I think, the intended solution. So let's look at it. We simply have to call a recursive function. We have to check if it's a wall, then we cannot go there. If it's a dot, then we can go there, and we have to keep on recursively calling this. But obviously, if we don't write this line, then it will be a problem, as I said. So we memorized it and solved it. Pretty simple so far. And basically it's an n to m, so that will be solved in it. Okay, now let's get to some fun problems. Anyone has any doubts so far? Okay, so let's talk about partition problem. Okay, so this is a fun problem. So what's the statement? Given a list of n matrices and the dimensions, it is given that they can be multiplied in the order given. Okay, so we have n matrices which can be multiplied. Find the minimum cost of multiplying these matrices together, given that multiplying two matrices of order AB cross B into BC takes ABC operations. Okay, okay. So so it's a fun problem. What are the constraints? N is 500 and order of matrices is 1000. Okay, so let's look at this problem. Okay, so first of all, let's look at the problem and try to understand what it's saying. Suppose we have a few matrices. Wait a second. X. So, and we have some order. We are given that they can be multiplied. This will be like this. Okay, so now we have to multiply them in some order so that we get an optimum number of operations. We can clearly see that if we choose different orders, then the final number of operations can be different. We can like write down the expression for different orders and see it is different, but it is clearly visible also. So like if we choose y and then choose z, if there is also one more, let's add one more. So choosing different will lead to different final number of operations. So how can we do this problem? First of all, there like okay. So how can we do this problem? First of all, there is one very obvious and trivial solution of 2 to the power n. How we are going to do this? It's obvious that we will. Oh no, sorry, not 2 to the power n of n factorial. Uh, we have actually it's n minus 1 factorial, but it's fine. So we have n minus 1 joining points, and we will just assume some order of joining, that first I do this, then this, then this, then this, then, and then we can just permute over all of them and get our answer. So that is obviously a solution, but that won't pass. As we can see, n is 500, so n factorial would be very large. Now what else can we do? What we can say is that one thing we can clearly observe is that suppose if I have a subarray and I decide that I will join this at the end, then I just have to find the optimum answer for this and the optimum answer for this and then join them here. Using this observation, we can see it is similar to the first question in which we were solving for all the subarrays. So over here also, we can think that if we solve for all the subarrays, we can come to the final answer. But the problem is that we made this choice that we will make the join here at the end. So as we cannot decide which join will be most profitable, one obvious way out is to check for all of them, i.e. assume every possible join to be the end join ones and get the best answer out of all of them. So to calculate the answer for any subarray, I will have to do at max n operations, and there are n square subarrays. So my final answer will be of n cube time complexity. And we know that 500 cube is 125 E6, i.e. 1.25 E8, that will pass. Okay, so let's look at the solution. So we will first of all take input for all the values of orders, and then we will iterate. Once we will first iterate left end from the right end, because we don't want to, because we are writing iterative DP, we don't want to encounter a situation where the states we require are not already solved. So we iterate our left pointer from the right end, then we iterate our right pointer from this left end, and then for every subarray we can solve the answer using another for loop for the joining point. So this will be n cube, and final answer will be the answer of the whole DP. So like you can look at it once. Like the fun part about it is that the only observation is that we can join the answer of two subarrays just if we can join the answer of two subarrays by just deciding the joining point, then we can simply calculate the answer for the whole array in n cube. No other observation was used in it. If anyone has any doubts, please do tell. Okay, so let's continue. Yeah, it will be solved in n cube. So LIS in n log n. Okay, so this is one of the most fun and important problems, as this is a very frequently used observation, and this further builds upon two more advanced techniques also. So let's learn this. Okay, so the question is simple: find the longest strictly increasing subsequence in the given array, and but we have to solve this in n log n time, as n is 1e6 and ei is 1e9. So we are already familiar with the problem. I will quickly reiterate that we have an array of elements. We have to find the longest strictly increasing subsequence, and we already know that there is an n square solution in which we join an element with the longest subsequence till now which can be joined with it, as discussed in the previous lecture. Okay, so this looks quite optimum already. How can we optimize this even further? Okay, so there are quite a few ways to do this, and let's reach upon them using observations. What I am going to say is that whenever I add a new element, I am trying to find the largest answer that exists before this element, which was associated with an element smaller than our current element. So uh, we can see that it is possible to do so if we maintain a data structure which can quickly give us the element and the corresponding answer which has the largest answer and is smaller than our current element. So what data structure to use and how exactly can we do this? To understand that, let's look at what we will have in store with us. So we will have some elements and some answers. Straight away, we can make two observations. First of all, is if the elements are in sorted order, i.e. if I store them in sorted order, they are not necessary to be sorted in the array, then the corresponding answer values will also be in sorted order. Why is this true? I can say this because let's assume that C was greater than B, but the answer of C was not greater than B. Then we can obviously say that C is completely useless. Why can we say this? We can say this because right now B has a better answer than C. Suppose C ends up being the best answer. Then I can automatically say that same can be achieved with B because any element that comes after C will be greater than C. And as C is greater than B, it will also be greater than B. So whatever answer I can create with C, I can also create with B. And as the current answer of B is bigger, we don't need C. With this observation, we can conclude that if elements are kept in sorted order, their answers will also be kept in sorted order. One more observation I can do is if I store in the sorted order of by the way, why are we thinking to keep them in sorted order is because we need greater than some value or less than some value. So it can be beneficial to think in this manner. Okay, so if we keep the answer in sorted order, we can say that the values we are going to have to the corresponding uh, answers will also be in sorted order, obviously, as I explained above. So either of these can be useful. Let's look at this in detail first. How can I find what I require quickly using this? So what I'm going to do is I'm going to look. What I have to do is suppose my element is X and X lies here. Then out of all these elements, I need the one with the maximum answer. But I obviously know that this value will be the maximum. So I just have to search for the element just smaller than X and get the value, and we can say that its answer will be this value plus 1. After then I can insert it here and I can check if the answer of C is better, then C can stay, or else I can remove C to maintain monotonicity. So if I keep on doing this, then at the end this will be my final answer, the end element of my set. This so okay, so is this clear what we have done in the first method? Okay, so like with this, as the time complexity of inserting into a set, oh, okay, if it's not clear, then I will explain it again. Okay, so, okay, I will start with the observation. Okay, so I think this observation is quite clear that if I will keep, okay, let's roll back a little bit more. What I'm doing is what I did in n square was I searched, I knew the maximum possible subsequence ending at a particular element. I was storing them for all the elements, so I knew the answer for all the elements before this. In the n square solution, I simply checked all the elements that were less than a, found the maximum answer. So the answer of a was that answer plus 1. That is what we were doing in the n square solution. Now, to optimize this, what I'm saying is that instead of just storing the answers in the initial array at the element itself, we can store them at a separate place in a data structure form so that this searching is quicker. Because if we just store them here, we will have to check every element and find the best answer. So what I am trying to do is store them in such a way that this checking can be accomplished quickly. Now when I am storing them, I am planning to store them in a sorted fashion because I want to check all values that are less than my current value. So maybe keeping it in a sorted fashion can help us. Now what I have done is I have stored all the answers before this in a sorted fashion and I have made an observation. The observation is simple, that if my values are in increasing order, then their corresponding answers also have to be in increasing order. If they don't follow the increasing order, then I can simply say that that value is never useful. As I explained here, that suppose the answer of C was not greater than B, then I can simply discard C because C can never give a better answer than B. Or at least B can give as good as an answer as C, because everything that we can add at the end of C can be added at the end of B. Okay, so our optimal answer won't change, so I can just ignore C to keep this monotonicity active. So the conclusion we reached was that if our values are monotonic, increasing, then the answers will also be increasing. How is this helpful is, when I want to search this region and get the maximum answer, I just have to see this. So in my set, I can just check the answer corresponding to the value just less than B. Get this answer, add 1 to it, and we get the answer for X, our new value. And then we can repeat this process by inserting X and checking if C is still valid, i.e. the answer of C should be greater than this. If it is, then it's great. If it's not, then we have to delete C and so on. So as in, searching and inserting and deleting from set all takes log n operations, this is n log n. Okay, now let's look at the other way. What if I did store it like this, that for each answer I am saying that if answers are increasing, then the values should also be increasing. What am I going to do if the value corresponding is not increasing? Well, I can simply do it like this, like I was doing in it, and it will be the same solution. But if I look more closely, I can make a very interesting observation that this situation where the elements are not in increasing order is actually impossible. And why is that so? That is because suppose initially I have this and I added an element and I have x. This x will belong somewhere and the answers will be increasing. Let's assume one more important thing, the answers will be continuous because obviously every answer is possible. We cannot reach 6 before reaching 5. We similarly cannot reach 3 without reaching 2. So every answer will be there. So what I'm saying is that suppose I have x and I take x and I insert it. Now x will go at some position. Let's say is greater than c and less than d. So less than equal to d. So it will come between here. What will be the answer for x? The answer for x will be 3 plus 1 4. And as d will become useless now, I will just remove d, or I can say sorry as d will become useless now I can remove d, or we can say that we can simply replace d with x as x is less than equal to d. In this scenario, the monotonicity is always maintained because we know that the answers will be in the increasing order and x will only be inserted at the position where it belongs. So monotonicity can never be broken. Let's also prove this by contradiction very quickly. Let's assume that monotonicity was broken and I inserted x over here and e was not greater than or equal to x. That means that e was less than x. In that case, x will not be inserted here, x would be inserted here. So we have proved that the value after x will have to be greater than x. Okay, so as we just saw, we don't need any set for this. We can simply make an array and we can, okay, I will show you. We can simply make an array where the ith index corresponds to the answer. And we know that the elements will be in the sorted order. So we just have to do a binary search and find the correct position and put x there and so on and so forth. And at the end, we will see the maximum value we have reached. And that will be our answer. So we just saw two ways of doing this. Both of them are quite interesting as this is very easy to implement and don't requires any complicated data structure. And log n of set is also has a constant heavy constant factor. So this is faster. But this approach can also be useful as this later evolves into convexal trick if, after some careful observations. Okay, so this was LISN and login. Anyone has any doubt? Okay, so let's continue. Let's look at the solution. We have to iterate, and for every element we just have to binary search. Here we are using upper bound, and we will get the element, we will update the answer, we will keep doing so. Finally we will see which index we have reached. As we have initialized it with infinity, we will see the index which does not has infinity, last index. That will be our answer, and we will just return it. It will be done in log n because n iterations and every iteration takes log n of binary search, and we will be done with it. Okay. Okay, so let's get to Bitmask DP. Bitmask DP is quite fun as it's quite useful and can be counterintuitive at times. So let's look at it. So we have n people and their weights, and they want to ride in an elevator with the maximum capacity x. What is the minimum number of rides required to achieve this? So our constraints are 20, and weight of the capacity of the elevator is 29, and weight of each person is in the same range. Okay, so how we are going to do this? Let's first of all look at the problem in more depth. The problem in more depth. So what we have is, we have 20 people at max, and they want to ride in an elevator, and it has a maximum capacity. Every person can go individually, some people can group, but not everyone can go together. So we have to optimize in such a way that the wasted space is minimized, and we get an optimal answers on the number of elevator rides. Okay, so how can we do this? First of all, let's look at a naive approach. So what I'm going to say is that these people are going to go in some order. So let's assume they are going in some order. So there can be n factorial orders. And for each order, I can calculate the minimum number of elevator rides required very nicely, because I will just keep on adding people till I cannot add the next person, and then restart from zero and keep on adding and calculate the number of rides used. Okay, now how long will this approach take? Well, n factorial number of uh, permutations, and for each permutation O of n, so n into n factorial. Obviously I can optimize this by removing the n, as I can say that our ideal answer would have come in many ways. So suppose there is some person x, this person has to go sometime or the other. So let's assume he is the first one always, as there will be an optimum answer with this person x being the first one, and I will assume that he is the first one, and then just permute on the rest, and then minus 1 factorial will be permutations, and into n minus 1 for solving. But this is still approximately n factorial. So as n is 20, 20 factorial won't pass. We can quickly see the value of 20 factorial also. So okay, so 20 factorial is quite large. 1 2 3 okay, so it's 2e18. Okay, so that won't pass obviously. What can we do other than this? One hint that we can see coming from the problem is that n is 20. So it is possible to iterate over all the subsets of the number of people we have, i.e. 2 to the power n combinations, and we know 2 to the power 20 is approximately 1 is 6. So that will be possible. So thinking in that direction, I can say that suppose we can be thinking in that directions. So what can I say when calculating the minimum number of rides for a certain group of people? I can say that the answer of this problem would be, let's assume that we take some set of these people, some subset of these people, and we put these subset in one elevator and add one and check the answer for the remaining subset. Like this subset does not need to be in order. Just 1 second. Like I took some subset and I put these people in the elevator and I checked the answer for the remaining people and added one to their answer. I can do this for all the subsets. So what I'm essentially saying is that in the first ride, some people have to go and I can iterate over those some people and I can find the answer for this subset. So what we conclude is, if we want to calculate the answer for any subset, for example, let's assume our subset is this, and I want to calculate the answer, so I will iterate over all its corresponding subsets. So as 4 bits are 1, it will have 16 subsets. So let's assume one subset is this. I will check if this subset can go in one ride. If yes, then I will add the answer of this to the answer of the remaining ones in this subset, i.e. 1, 1, 1 here, 0, 0, 0, 0 here. Okay, so 1, 0, 1, 1, 0, 1. Okay, so I will add the 1 to the answer of this subset, and this is our possible answer. And we will similarly iterate over all subsets, i.e. 16 possibilities, and we will take the minimum and we will get the answer for this subset. So to calculate the answer for one subset takes iterating over all its children. So let's suppose our subset is of size x, then it will be of 2 to the power x, and we have to sum over all subsets. Now all subsets. Okay. Now what I can say is that naively I can say that maximum size of any there are 2 to the power n subsets and maximum size of any subset is n. So if we iterate over all its subsets, they will also be 2 to the power n. So our final answer will be 4 to the power n. We have basically found a bound for our answer. So let's see if it is possible to do this. So n is 21, so 4 to the power 21 is this much. Sorry. Okay, so this is 4 to the power 12 and it will not pass. Okay, but if I think carefully, I can say that not every subset will not be of size n. I can also say that not only will every subset not be of size n, the subsets which are of smaller size will be huge in number, i.e. only one subset has size n, only n subsets has size n minus 1. Only n square nc2 subsets have size n minus 2, so on and so forth. So it is possible this number is actually much smaller. Okay, so what I can say is that let's calculate that number. It is actually the sum of 2 to the power I into nci for I is equals to 1 to n. And like if you solve this, you get 3 to the power n, which is obviously much smaller than 4 to the power n. Okay, we can also see this directly because like I will just quickly share how we can see this directly without any summation. As I can say that if I want to have a subset of a subset, then I have to choose two numbers, and in these two numbers I have to set bits, and these bits can either be 1 1, these bits can either be 1 1, 0 0, or 1 0. They cannot be 0 1 as it is the subset of previous number, so it cannot be 0 1. So for every subset of the subset, there are only 3 to the power n possibilities instead of 4 to the power n. Okay. Now let's calculate this number. So how much is 3 to the power n? 3 to the power n is this, and it is 1 2 3 4 5 6 7 8 9 10. It's 1 in 10. It's very close, but this will still not pass as we can at max run 2e8. So it's around 50 times slower than required. And just for information, 3 to the power n usually runs when n is 17. Okay, so we have made a few observations, we have come to a closed solution, but this is sadly not what can finally happen. Okay, so what observations we have made till now, let's revisit them. We have made the observations that if there is an order, then I can quickly calculate the number of amount for that order. What else I have observed is that for any subset, I can also find the answer of it by visiting all its subset. Okay. One more thing that now we can see is that as people will have to go in some order, we can say that the answer of a subset can be calculated in a different way. Let's assume this is our subset. To calculate the answer for this, I can say that some person would have to have gone at the end, because someone has to go at the end. Now I can iterate over that possibility. There are only 4 possibilities in this case, so I will just iterate over them. So let's assume that this was our answer, this was the last person. So I can look at the answer for this subset and I can say that please add this person now. And this way I can calculate the answer for each subset in at max n time. And as there are n into 2 to the power n, as there are 2 to the power n subsets, n into 2 to the power n will be a total time. This looks quite promising. Now how can I check quickly that will this person be able to enter the same elevator or will have to take an extra elevator. For this, I can say instead of storing the minimum number of elevator rides required for a subset to go up, I can store two things: the minimum number of elevator rides required along with the maximum space left in the last elevator ride. Now, why is this interesting and useful? If I do this, then whenever I have to check if this person can go, I can quickly check by just seeing if the size weight of this person is more or less than this capacity, and correspondingly I can make an answer. Obviously, this will be the best answer as no other answer can be better, and if the number of elevator rides is less for some answer, then I don't have to worry about the capacity, because in a way its capacity is this plus capacity of one more elevator ride. So less number of elevator rides is always better. So what we have concluded, so instead of storing for every subset what is the minimum number of elevator rides, we will be storing minimum number of rides and the maximum space left in the last ride. Using this information, I can conclude what will be the most optimum answer if this person was at the end. Because if this person was at the end, then it will obviously be the most optimum answer for this, and checking and adding one if required. Okay. Similarly, I can just iterate over all the possible last persons and get my final answer. So this runs in n into 2 to the power n. Let's see if it will run for n equals to 20. Okay, so this is quite a small number, which is 1, 2, 3, 4, 5, 6, which is 2e7, and yes, it will run easily. Okay, so we have solved the problem using this way, and this is a solution. So you can see that I have stored for every possible bit mask the two things: minimum number of rides and what will be the maximum weight left in the last ride. And then I just simply have to iterate over all the prefixes, and for those prefixes I just have to iterate over uh, all the values that are 1, and I can check the answer from before and update it, and finally the final answer will be the answer of the whole number, i.e. 1111111. Okay, so this will take n into the power n operations and will pass. Okay, so now we are at the last topic for the day, which is binary exponentiation. So this is a very fun and one of the most used things, and let's look at it. So problem is simple: find a to the power b mod c, and the constraints are a is 1e9, b is 1e9, c is 1e9. Okay, so let's look at the problem. Okay, so obviously I know straight away one very naive solution that I just have to multiply a with itself b times. I just have to multiply a with itself b times and keep taking mod, and I will be able to solve this in b operations, but that will not be fast enough. Okay, what else can I do? And to do this, we will have to go to our childhood and look what we used to do. We used to do multiplication tables. Why did we do multiplication tables? Because we stored an answer, and whenever we needed an answer close to it, we could use this and get to our answer quickly. Now we can do something similar over here, i.e. I can pre-compute and write in a vector the value of some values of a till 1e9. For example, let's suppose I wrote the value of a to the power 1e8, a to the power 2e8, a to the power 3e8, so on and so forth. And whenever I was required a value, I will start from the closest power of a that is less than it, and I will only have to multiply 1e8 times, and I will get to the answer. Now, this would have worked as 1e8 operations can work, but we don't know a also, so I cannot make tables. But I can use this observation, because this observation shows us that uh, storing the answer of some power of a might be useful. We can also do one more quick observation, which is that we are redundantly applying a with itself a lot of times. What I can easily see is, suppose that I have a to the power of 8. I can simply multiply a 4 times and do whole square once to get the answer, cutting my operations in half. Similarly, I can calculate a4 by squaring a square, and I can calculate a square by simply multiplying a with itself. So instead of multiplying a 8 times, I just have to keep on squaring the number thrice, which is much smaller than 8. Similarly, if it was, for example, 1024 instead of 8, I could have done this in 10 operations. I log of that. Now, this is quite an interesting observation. Using this, I can quickly calculate any power of a. So, what my approach will be, I just saw that I can reach any power of a that is also a power of 2 by simply squaring the number. Okay, I know that b is less than equals to 1e9. So I can say that b is less than equal to 2 to the power of 30. What this means is that if I want to reach a to the power of 2 to the power of 30, I can do so in mere 30 operations. So I think the solution is quite obvious now, that I simply need to maintain an answer. Let's fill it with 1 once, because we are multiplying and 1 is multiplicative identity. So we will write 1 here, and we will make a temporary variable which is initially a. We can write it like this, and we have b. What we need our answer over here to be. So I will just erase 1. I will write it in an interesting way. I will write it a to some power. Currently it is 0. Okay. Now what I am going to do is, I am going to multiply and let's write b in binary way, because we will see just in a minute. Let's assume b is 1 0 1 1 0 1 in binary. So what I will do is I will just square this once. Squaring this is equivalent to adding 1 here. So this will become 1. Now I can see that let's write it in a very much interesting way also. Okay, so what I require is a to the power 101101, and what I have currently is a to the power 1. After, let's assume initially we have a to the power 1. Okay, now we need this in our answer, so we can simply multiply it here and get 1 and square our number. Because we are squaring it, we will multiply it. Basically squaring is multiplying it by 2, so we can also represent it with bit shift as we have seen. So we will just write it like this. Now do we need a to the power of 2 in our number? No. So we will not multiply it to our answer and we will square it, i.e. bit shift. Now do we need a to the power of 4 in our number? Yes, we need it. So we will multiply it with our answer and get it this and square it again, and we will keep on doing this process until we get our number. And we have already shown this squaring process can never exceed 30. So every operation will be completed in 30 operations. So basically we have achieved this in log n. The code is also quite trivial, as you can see that we just have to make a result and make a value b, and we have to basically complete b, so we can do it in the reverse order also, like keep on subtracting b and removing things from b, and we can get our result. Okay, now let's talk about matrix exponentiation. So matrix exponentiation is similar to binary exponentiation, and let's look at it with a problem. The problem is similar to what we did in the first lecture. Find the nth Fibonacci term, only this time n is 10 to the power 18. Initially we did it in 2 to the power n, which is, as you can see, absurd, and then we did it in O of n, which is also not possible now. So what we need is to solve this problem quicker than that, and spoiler alert, as we are learning exponentiation, we will do it in logarithm time. Okay, so how we are going to do this is I only have one information with me, which is this. Now thinking in the same line, we cannot just over here we were accumulating A's and increasing our accumulation continuously, but over here we cannot accumulate something which is a recursive function. But in reality, when talking about finite term linear recurrences, there is a simple method to achieve the same result, same situation as multiplication, as we all know, which is matrix. Okay, so what I can say is that I have two terms, A and B, which is the last two terms of my sequence for now. Now what I'm going to do is I'm going to find the next two terms. So I can say the next terms are B and A plus B. They come out of a linear recurrence, so I can write it as being equivalent to multiplying it with a matrix with the first term now being the sum of the first two terms and the second terms being the first term which was the previous first term. Okay. Okay, so what I've done is, so after multiplying it with this matrix once, we will get that whatever result we want, which is a plus b and a. Okay, so this is what we required and this is what we will get. Sorry. Okay, so similarly we can see now the complete process has become obvious, that we just have to, for getting next term, we will simply multiply again and simply keep on multiplying. So in essence what we are doing is, to get nth term we will have to do the power n minus 2, because like this is the first term, this is the second term, and after multiplying it once we will get the third term, so and so forth. Okay, so now we just have to find this matrix, and this matrix is simply the previous question, that what is a to the power b, and we can solve it in the same manner. Yeah. So in essence we have solved all the finite term linear recurrences in logarithmic time. But just for practical purposes, be careful that this term should usually not exceed 3 or 4, as we are multiplying matrices and they take n cube time to multiply depending on size. So if like you have 4 terms, you will get a constant factor of 64. So yeah, just be careful with it. That's okay. So let's look at the code. It's quite similar. I've made a struct matrix and I've overloaded multiplication, and then the same code for as I had used in binary, and then after that the code is simple. Okay, so that's all. It will take log n. That's all. Okay, so if anyone has any other doubt, please do tell me. Okay, so with this, the lecture is over. Thank you all for coming. Next will be problem solving with dynamic programming on 28th.